Welcome everyone. So this is our 55th live stream geometry. We have 3 people here with us so far, and I'm guessing more are probably going to join later. So if you'd like to join a future session, feel free to email me at mgreenb801@gmail.com. It's in the description of the video, and we meet every Sunday at 8 a.m. US Central Time. So today I'm going to go over the USAJMO. So the USA used to have just one main math Olympiad, but then around maybe 2012 or so, maybe a little before that, they split it into 2 competitions. One for, I believe, 9th and 10th grade, and the other for 11th and 12th grade. But I think if you did enough on the qualifying tests, some of the 9th and 10th graders could take the ones for 11th and 12th grade. But anyways, this is the junior contest, and maybe in a future video I'll do the senior contest. All right. So here's the first question that I chose. So we have a cyclic quadrilateral with perpendicular diagonals. All right, so I'm going to draw that. Okay, so we want AC perpendicular to BD. So I'll just call this O for now. And see, we have someone else join. So A, I'm just going to let be any sort of point here. So we have AB. Let me draw segment AC, and then I'll draw BD perpendicular to it. So here is AC, and then here's BD. Another person just joined. So yeah, thanks for joining, Vanch and Serdar. Just to catch you guys up, I'm taking problems from the USA Junior Math Olympiad. Let me make this just a segment instead of a line. And E and F are the reflections of B over BA and BC. Okay, so I'm going to want to draw those as rays. There we go. So I reflect B over both of those. BA and BC. Let me call it E and F. So this will be E, and this will be F. I kind of like these double reflection problems. I feel like there's a couple of them. We got a lot of people hopping on. So P is the intersection of BD and EF. So USAJMO problems are usually a good bit easier than USAMO problems. But this one looks kind of involved. So we draw the circumcircle of EPD. And it meets omega at D and Q. Okay. I see M Aria just joined. Are you new to this, or have you been on before? So this is Q. New. Well, welcome. Thanks for joining us today. Yeah, feel free to share what country you're from if you want, or you don't have to if you don't want to. So Q is the India. All right. We got a few people from India on the channel. So let's see. Oh, Stefan, you think you already saw it? Okay, well, you can give us hints if we get stuck. So you have the circumcircle of EPD and the circumcircle of FPD, and that meets omega at R. It almost looks like it's B. I don't want B and R to look like the same point. Wait a sec. Oh, because I did BPC instead of FPD. So this one meets the circle at a point R. And we want to show EQ equals FR. So whenever you have equality of segments, I often think about like congruent triangles. So maybe we can find some congruent triangles. I want to show EQ equals FR. And I wonder, is this an isosceles trapezoid? I don't think so, but I'm not sure. Maybe it is. Let's see, how would I check that? I like to check if it's cyclic. Yeah, that looks like an isosceles trapezoid actually. So that's really what we want to show. Interesting. Okay. So can we show QR is parallel to EF? Let me draw DE and DF. Is DE tangent to that circle and DF tangent? Looks like it. That's probably an angle chase, I'm guessing. So let's say we know by an angle chase that DE and DF are tangent. Oh no, DF isn't necessarily tangent. You can see it right here. Okay, so they're not necessarily tangent. Maybe I'll just move things a little bit just so that it's more obvious. I kind of wonder if these two are equal and it's cyclic, then yeah, that has to be an isosceles trapezoid. Okay. I'll just have to remember that these aren't necessarily tangent. Okay, so this is the midpoint of ED right there. And this is the midpoint of DF. So BGDH is cyclic. I don't know if that really helps too much. So yeah, how do we show that these are parallel and that this is cyclic?
I guess A and C are the centers.
A and C are the circumcenters of these, right? Is what you're saying, right?
Yeah.
Because let's think about that. So we know AE equals AD. And is it obvious that AD equals AP? P is a reflection of D across AC. Okay, so we're using the Simpson line. I guess what you could do is you could, if you know AE equals AD, you could consider the circle as center A passing through E and D. And if you let it intersect at a point, you could try to show that that point is the same as what it would be for point C. But yeah, or maybe we could just use Simpson line. Let's see. So Khan's saying by the Simpson line, P is the reflection of D across AC. So is that the Simpson line?
Simpson line is GIH.
GIH. Okay, because those are the
Actually, EF is the standard line of triangle ABC.
EF is the what line?
Steiner. Have you ever heard about Steiner line?
Oh, Steiner line. Does that have anything to do with the orthocenter? I'm not 100% sure. I don't. It passes through the orthocenter of ABC, and is there just one Steiner line, or there's like a Steiner line for like every point on the circumcircle? Yeah, okay. So P is the orthocenter of ABC, and EF is the Steiner line. What makes EF the Steiner line? I've never, I think I've heard of it, but I'm not sure what it is.
If you perform OTT with center D with ratio 2 to Simpson line, then you have Steiner line.
Ah, okay. So GIH is the Simpson line of D, and then you perform a homophily with ratio 2, and then EPF is the Steiner line.
Yeah.
Okay. Interesting.
And this is through orthocenter.
Okay. So I think I actually might have heard it. Oh, I think I heard it the other way. So like, let's say you have a line through the orthocenter, like EF, and you reflect it across the three sides.
Yeah, it's the anti-Steiner point.
Yeah, that's the anti-Steiner point. So I'd heard of that, but I didn't realize it's like the other way too. You just call it the Steiner line. Interesting. Okay. So that means, what if we draw DQ? I wonder if it passes through that point right there. Looks like, yeah, it looks like these concur and these concur. And I think that's true by that property of like the Steiner, anti-Steiner point. Because the reflection of this line over the three sides of ABC all should concur at point B, right? So that would make sense. So we know angle QJB is BJK. We have a lot of different equal angles here. Okay. So I feel like we're getting a lot of information here. So, okay, so we have angle EQP is QDB, and we have angle RFP is RDB. So, but then this, so yeah, this is like, DB is like an angle bisector here, right? Because is that obvious? DB bisects angle BQR. So that would prove that those angles are equal. Then I'm kind of skipping a few steps in my mind right now, but I think we'll be able to show that angle RFE is angle QEF. But then if we want to show it's an isosceles trapezoid, we would have to show something else too. ABC are the midpoints of arcs QR. Yes. I'm not sure how to prove B. So it looks like RPA and QPC are collinear. Not positive, but yeah, there's just a lot of stuff in this diagram going on. So P is the orthocenter of ABC, but it looks like it's also the in-center of QDR. So yeah, I want to show EQRF as an isosceles trapezoid. I think it's not hard to show that these angles are equal. But then I would also need to show that this is parallel to this. But maybe it's, I don't know if it's obvious somehow. We have to use that AC is perpendicular to BD. Oh, we kind of used that already. We could show, yeah, we could try to show those angles are equal to, right? Well, yeah, because angle EQR is EQP plus RQC. And I think maybe that's good enough because EQP is 180 minus EDP. Are EQ and B collinear? No. Oh, I think they are. Whoops. Looks like EQ and B are collinear. And yeah, so I mean, if we have all this information right here, that should be more than enough to solve the problem. It's just figuring out, yeah, what order do we prove things in? Yeah, okay. So, I mean, if we know BQR is isosceles, then yeah, this has to be an isosceles trap. I mean, BQR would be isosceles and BEF would also be isosceles. So, yeah, I think now it's just figuring out how to write it up in the right order. But yeah, I don't think this is like a super tricky problem. Okay, so let's see, what's the best way to start? So first, GIH is the Simpson line of D with respect to triangle ABC. So I'll say let G and H be the midpoints of DE and DF. And I'll say let I be the intersection of AC and BD. Then GI and H lie on the Simpson line of D with respect to triangle ABC. Okay. So then EPF is the Steiner line of D. I'll say a homothety with factor 2 of that line implies E, P, and F are collinear.
We defined P so that it is collinear, so you can't say that.
Oh, that's right. Yeah. So this basically would, yeah, show that P is the orthocenter. So take, I'll say homothety with factor 2 of that line takes it takes I to P. Whoops. So it takes I to P, and that implies P is the orthocenter of triangle ABC. Good point. So that proves that P is the orthocenter because the reflection of the orthocenter about the side lies on the circumcircle. So if you do it the other way, then it has to be the orthocenter. Okay. And once we know that P is the orthocenter, then I'm guessing it's not hard to show that P is the incenter of QRD, but I mean, I'm guessing that's an angle chase, right? Because angle QDB is QCB, and angle BDR is BCR. Wait a second. We don't know CP and Q are collinear. Oh yeah, that's true. So let's yeah. I'm gonna hide everything we don't know, and then I have to prove it all. So we don't know that yet, and we don't know this yet. But we could start by saying this, P is the orthocenter. I don't think I've drawn anything else. Actually, we don't really know that these concur, right? So I kind of just drew that. But I think we can use facts about the, let's see P cut the circle at Q prime. Okay. Yeah, that's a good point. So I kind of like that. So let's see P cut the circle at Q prime. And now we want to show Q prime PDE is cyclic. So let's see. So we have, since P is the orthocenter, Q prime is a reflection of P across AB. But how do we know that CP is perpendicular to AB? Is that obvious? Oh, because P is the orthocenter. Yeah. So, yeah, you're right. So, okay, because well, yeah, because we know AE equals AD. And how do we know AQ prime equals AP? Oh, because yeah, AP is equal to AB by symmetry. So, okay. So AQ prime equals AP equals AB equals AE. Implies Q prime PDE is cyclic with center A. All right. And that implies Q prime equals Q. See if this all fits on one line. It did. It's nice. All right, so we have Q prime equals Q. So I could, and then, so basically Q, P, and C are collinear, and then similarly, yeah, similarly, so I'm going to draw on that circle. So similarly, we have R, P, and A are collinear. All right. And so we can draw that circle. What is it? RPDF, yeah. Then we have that. And Is it obvious that, okay, so is this enough to show that P is the in-center of QDR? Let's see. Because, how do we know A is the, because we know A is the midpoint of arc QD and C is the midpoint of arc DR. Yeah. So, because of what we said right here. So A is the midpoint of arc QD. And C is the midpoint of QR. So that means that P is the in-center of QDR. Then once we know that, okay, so by symmetry, we should have B, Q, and E, and B, R, and F are collinear. Because, is that an angle chase, or is that just like obvious by symmetry somehow? Because angle BQC is BDC. So it's the same as saying BDC is BDE, right? If you reflect line BPD across BA, okay, yeah, so I like that, by reflecting line BPD across BA, B, Q, and E are collinear. And then similarly, B, R, and F are collinear. Here, all right. And now we are very close. So I'm going to draw in those segments. And then BQR is isosceles because B is the midpoint of QR. And then also we know probably by an angle chase BRQ is BFE, I'm guessing. Yeah, yeah. So B, Q, and E are collinear because B, P, and D are collinear. And if you reflect both of them across line AB, then you get B, Q, and E. So that's why it's like, yeah, this whole triangle BDE is isosceles, and Q and P are reflections, and B and E are, yeah. So it's easy to get QR as parallel to EF now because we have yeah. So angle BRQ is BDQ, BRQ is BDQ. And then that's equal to angle BDR, which it's BDR, which is PDR. And then PDR is PFR. So we have EF is parallel to QR. All right. And so both BRQ and BFE are isosceles, so FR EQ equals FR. So I'm just going to make a little bit of room here for one more line. Let's see what I can do. Move that up, that up. So I'll say BQR and BFE are both isosceles. And that means that EQ equals FR. All right. Sounds good. Thanks everyone for your help on this. It's not the hardest problem, but it was a fun one. So we'll move on to the next one. Okay, this is interesting. So here's a problem with an equilateral triangle. So this one is from 2017. So I guess what I'll do, I'll just do something like this. So ABC, whoops, ABC is equilateral. And I can hide these two now. And P is at any point on the circumcircle. Whoops. Make it bigger in just a second. Oh, I think I'm going to want to draw the lines actually, not just the segments. So, okay, so P is a point on the circumcircle. Call this P. And then we draw PA, PB, and PC. And we see where it intersects the opposite sides. And then I don't do a lot of problems with areas, but here's an area problem. So let's see. We want, we can see PA intersect BC. We can see PB intersect CA. And, oh, okay. Yeah, there we go. So we have all the points right there. So that's not so bad. So this is D, and then PB intersects AC at E, and then PC intersects AB at F. We want to show the area of DEF is twice ABC. So I'm going to hide a bunch of unnecessary lines and turn them into segments just to make things look nicer. All right. Whoops, I should do this. EAC, CBD, this. So it looks a lot kind of like Ricard's theorem, right? And we want to look at the triangle DEF. So yeah, I don't do a lot of equilateral triangle problems on my channel, and I don't do a lot of area problems, but this uses both, so it should be interesting. All right. We could use GeoGebra just to check that's actually true. Let's see. So the area of ABC. Oops, why is it giving me the area of like a single point? Area. What I could do, isn't there like a polygon? Let's see. Oh, this. So I could draw those two figures. And then just check it's true in GeoGebra. Oops. There we go. Then we have the area of this, 10.23. Yep, this is double that. All right. Yeah, because they were rounded to 2 decimal places. So that's why, yeah. So I'll draw the center of ABC. Call it O. So F is the orthocenter of OED by Bricard's theorem. Because ED is the polar of F, so yeah, OF is perpendicular to ED. And then we can use
draw the intersection point of OF with ED.
Okay.
Of course, that would be the altitude of DEF.
Yeah. So,
but also I think that that intersection point is the Mikkel point of ABCP.
Okay.
But not sure how it should prove it.
So that would mean like we'd have a couple of cyclic quadrilaterals. So yeah, so OFG are perpendicular to DE. And yeah, I think it is well known. I feel like I've seen it so many times. So yeah, we would have a lot of different cyclic quadrilaterals. And then I think this should be cyclic. And then, yeah, I don't know if I need all of these, but. I'm just going to draw those two. We can just keep in our memory that the others are cyclic. So, yeah, so we have the Mikkel point of that quadrilateral. It is a well-known property. I forget the proof of it.
Probably an angle chase, if I would say.
Yeah, probably. So how do we get the area? So I'm thinking for the area of DEF, maybe it's easiest to like subtract things. So maybe I could like do the area of EABD minus EAF minus BFD. Let's see. So yeah, how do we relate the areas? So as P moves along this arc, what happens to the area of so the area of DFE should be the same apparently, but I wonder if the area of this whole quadrilateral stays the same. I don't think so, because like once we have it like this, then it looks like that would be like have a really big area, right? So is there some relationship between AE and BD? I don't know if like their product is the same or something. And also by Ptolemy, we know that PC is PA plus PB. So maybe that's useful. Oops. let's see. So we also have OF times OG is OA squared. Oh, by poles, by the theory of pole and polar, because ED is the polar of F. That's true. So triangle OFA is similar to OAG. And OFB is similar to OBG. Actually, we have as many similar triangles as we want, but yeah, I wonder if there's some relationship between AE and BD. Can I let EF and BF cut BC and AC? Yes. So maybe H, O, and I are collinear. I'm not sure. Just to see in just a second. Looks true, but let me test it. Yeah, that's interesting. I don't know if that's Pascal's theorem that we could use to prove it. Because it feels a lot like Pascal's theorem. Like if we draw the antipodes of B and A, let's say like this. Then we want to show B, I, and P are collinear. And we want to show A prime H. So yeah, it feels a little bit like Pascal's theorem that I, O, and H are collinear. Let's see, is it obvious? So saying that B, I, and P are collinear, what is that equivalent to? For B prime, I, and P? Is IHDE cyclic? Let's see. No. So basically, I guess that's the same as showing angle BPI is 90 degrees. So yeah, can we show angle BPI is 90 degrees? And similarly, APH would be 90 degrees. And I wonder if OH is equal to OI. I don't think so, but that would be interesting. Yeah, it's not true. So yeah, if we can show IPB is 90 degrees, then that would mean I, O, and H are collinear. I don't even know if that helps for this problem, but yeah, we do have an equilateral triangle. I feel like I haven't used that very much. So that should, I mean, so yeah, both these are 120 degrees. This is 60 degrees. We have a lot of information we haven't used. So APE is 60 degrees and BPD is also 60 degrees.
AOBG cyclic.
AOBG is cyclic. Okay. And that's probably just an angle chase, right?
Yes.
And so GEO is the bisector of AGB. Because yeah, we know angle EPD is I think is 120. Yeah, EPD is 120 degrees. You do have a lot of information here. You just have to figure out how to use it. I wonder if AB is the angle bisector of these two. No, it's not. So AP, BP, and FP are the bisectors of FPE, FPD, and EPD. All right. Yeah, because FPA is 60 degrees. Yeah, so there's a lot of angles that we have here. So yeah, how do we start with triangle DEF? It's the best way to do it. So yeah, PA plus PB is PC. Yeah, I still like the idea of using a subtraction. I just have to figure out how do we get like what is it exactly that we want to subtract? So triangle DF, we know F is, like you said, F is the orthocenter of ODE.
I know how to prove that PI and B are collinear.
Okay, how do you do that?
We'll know that E, I, A, and C is isogonal, harmonic conjugate, right?
So yeah, we know that.
So IA over IC is equal to EA over EC, and so E is equal to PA over PC. Someone tells that AP is angle of FPE.
FPE. So yeah, AP is the angle bisector.
Yes, and so PI is an angle bisector of CPA. So PI and B prime are collinear.
Oh, because B prime is the midpoint of this arc. I see how it works. And so you calculate AI over IC, and you can show it's AP over PC. Interesting. Okay, so those are collinear, and then those are collinear. And so by Pascal's theorem, IO and H are collinear. So, and then Hakan said CA over AE is PC over PE. Okay. All right, so I feel like we're making some progress here. So yeah, what's the right way to think about triangle DEF? So we know the area is FG times DE over 2. Is that the right way to think about it? Yeah, we really need to just find something about AE and BD. So like we have sine 60, because APE is 60 degrees. So sine 60 over AE is sine PAG over PG. And then sine 60 over BD is sine PBG over PG. So if you divided those two, you kind of get AE over BD is sine PED over sine PDE, which is PD over PE. Yeah, PD over PE. Yeah. So CA over CE. Oh, so yeah, that's kind of how you apply. Yeah. So and then once we know all that, it feels like we're really close because PC is PA plus PB. So yeah, I wonder if once we start writing the algebra, if it might start to make sense a little. So okay, so the ratio of the areas of AFE to AFC, it's going to be CA over AE. I kind of think I have an idea here on how I might want to do this. So Yeah, I wonder if once we start writing out the algebra, it might make sense a little bit. Because I feel like those ratios are like a good start to proving this. I feel like it might just be solved once we write it out. Let's see. You see how to do it now? Yeah. So let's start writing some of this out. So, oh, you see my idea? Yeah. So we have the area of CED is equal to, so brackets will be area. So that's the area of ABC times CE over times CE over AC. Times CD over BC. So we know that. And obviously AC and BC are both equal to a side of the triangle. So maybe I could just call that S. I'll just let S. But maybe it's better to write this as because CE over AC is 1 plus AE over AC.
Yeah, we solved the problem.
Oh, do you think you've solved it?
No, I asked if we have solved it by now.
No.
Okay, then I should just tell some of my observations. I think that AB is tangent to AEGP, and
Okay.
similarly the other circle. And so if that is true, I think that is an angle chase. Then GP would pass through the midpoint of AB.
Interesting.
And
okay.
Because of this median, then AGC, that angle would be equal to BGP.
Okay. So AGC would be BGP or APC.
AGC BGP. Yes.
Okay.
Don't know if it helps, but that's it.
Could. And I wonder, let me draw the circumcircle of DEF. I don't know if it passes through J or something like that. No, it doesn't.
Oh yeah, one more thing. Draw the tangents to the first circle through B and through A and B. Yes, that circle. Then it passes through that point.
Interesting. All right. So that's by Pascal's theorem. Let me just draw the segment. Okay, so the tangents to that circle meet on DE.
I think some wrote that it can be by Pascal's theorem proved, but I proved that using the polars.
Okay. All right, so CD over BC is 1 plus BD over BC. And we know these two ratios. So AE over BD okay, so that's the area of CED, and then maybe we can calculate the area of AFE and BFD. Yeah, because basically sine 60 is equal to sine 120. So yeah, so AE over AC. So yeah, I'll write this out on the next line. So this is ABC times 1 plus PA over PB times 1 plus oh, sorry, not PA over PB, but I think you wrote it before. So AE over AC is PE over PC, I think. And then this would be BD over BC is PD over PC. Oh, you think it might be better to write it the other way. Okay. And then the thing is AFE is equal to the area of it. So we have, so I was thinking CED. Yeah, I was thinking we take CEE and then subtract ABC, AFE, and BFD. Maybe that's a lot of work. I don't know, but yeah. So the thing is, we have AFE. Basically like sine of 60 is the same as sine of 120, right? So AFE has a 120-degree angle. ABC has a 60-degree angle. But this, so yeah, the area of AFE is AF times AE times, yeah, exactly. So I'm just trying to avoid writing square roots, although maybe I'll just do it eventually, but we could just say it's ABC times AF over BC times or AF over AB times AE over AC. so yeah, a lot of the things are equal to a side of the triangle. So we have AF over a side and AE over a side, but so AE over AC, we kind of, maybe it's just easiest to leave it. But yeah, how do we get AF? That's the thing. So yeah, maybe it's worth like expanding this out right here. But yeah, so I'm gonna write BFD also. So we have the area of BFD, it's the area of ABC times BF over BC. And then times BD over BC. You know, maybe I should just write, yeah, I'm going to write both these as ACs to make it easier. So yeah, basically we want to take this minus this minus this. And then so I think things kind of cancel pretty well because, well, maybe it's a little trickier. Yeah, that's my goal, is to kind of, yeah, subtract them. One sec, guys, I'll be right back. All right, let's see. So I'm back. Thanks for waiting. So yeah, there's some expression. And the thing is, we already have an ABC times 1 here, right? So, I mean, really, we want, let's see, AF. Yeah, I'm not sure how easy it's going to be to combine those three. So if we just call AC and BC S, I mean, that would probably be easier, right? So we have AF, AE, BF, and BD. Yeah, we could let them all be 1. Yeah, let's just do that. If they're all 1, AC, AB, BC, and AC, then we want to show that AE plus BD so assume AB equals BC equals CA equals 1. Then we want to show AE plus BD plus AE times BD minus AF times AE minus BF times BD is equal to 1. So we've turned it into an algebra problem. And the thing is AE minus AF times AE, because if we factor out the AE, 1 minus AF is BF. So wait, is this really BF times? Yeah. So it looks like this and this would cancel, would cancel out with that. And then we have BD times 1 plus AE. Wait, something's weird here. I don't know if I'm missing something. It's correct. Okay. So basically, if we factor out an AE, we get AE times 1 minus AF, and 1 minus AF is BF. So that would be BF times AE. AE plus, I'm not even going to simplify the next one. I'm just going to write it out. So see what that looks like. So I just took the AE and the AF times AE, and I combined them, and I kept the rest the same. So BF times AE, and then okay, I'll combine this one too. So 1 minus BF is AF. So this would be AF times BD. Wait, this doesn't look, oh yeah, this is symmetric. So let's see. BF times AE plus BD times AF plus AE times BD. We want to show this equals 1. Is that true? Because it looks like AE and BD are both. Yeah, is that right? I'm not sure. It almost feels like this would be bigger than 1, but maybe it's not. So BF plus A, we know BF plus AF is 1. Yeah, it's the AE and BD. And wait, we have those ratios. So AE is PA over PB. I don't know if it would help to write it because AE would be PA over PB. No, I'm sorry. AE is PE over PC. Oh, maybe this ends up using Ptolemy because AE is PA over PC. And AF is oh no, it's PE over PC. So let's look over this one more time. So I do everything right. A, B, C, and P. Okay, so AE is PE over PC. We just don't know what is BF. We don't know AF and BF in terms of, oh, but I guess we could figure that out by similar triangles, right? So AF and BF, how do we, or AF over BF is PA over PB. Oh, that's true. I didn't even realize that. Okay. So that's just the angle bisector theorem. But that's the ratio of the two. So like I could divide this by so we know the ratio AF over BF, but we don't know just AF and BF by themselves, right? But we know that AF over AP, well, AF over AP is CF over CB. But like we have, we need AE and BD. Sorry, Nguyen, I'm a little, so EA over EA is equal to 1, right? And BD over BD is equal to 1. Did you mean to write that?
Can we explain?
Yeah.
EA over EC is equal to BA over BC, right?
Is equal to BA over BC. EA over EC is PA over PC.
Yes.
Is this a right angle here? Is that so?
Yeah.
Oh, I didn't realize that. This is a right angle. Okay.
Yes. And DB over DC is equal to PB over PC, right?
Yeah.
So we subtract EA over EC and DB DC is equal to PA plus PB over PC is equal to 1.
To 1. I really like that. Okay. So let me write that out. So we know that EA over EC plus DB over DC is equal to 1. I think that might be the key to solving this. So we have EA over EC. Whoops, where'd it go? I'm going to write this out in a little more detail in just a second. I just want to check because I think this might be the key idea right here. Because EA over EC is equal to AI over IC, which is PA over PC. So, okay. Let me write this as, and then EA over EC is, that solves it. Okay. If we expand it out. So this is the same as, okay. So this is AE times DC. Let me just, to make it easier, do it like this. AE times CE, and then BD times CD. So this means that AE times CD plus BD times CE equals CD times CE. And then CD is 1 plus BD. One plus BD plus BD times 1 plus AE. Is equal to CD is 1 plus BD times 1 plus AE. So let me start a new line here. And that would mean if you expand this all out, then BD plus AE cancels. And then, so basically you have AE times BD equals 1. Interesting. Exactly. That's surprising to me. So this, wait, that doesn't make sense because this is 1. Something we did wrong. Yeah. So maybe this right here is wrong. It seems true that AE times B, like visually, it looks true that AE times BD would equal 1, right? So I think I have to look at this and kind of see what I did wrong. So let me delete the part with P right here. Make some more room. But yeah, if I combine all these, and then let's see. So I want to show that, wait, I want to show that when I subtract the 2, I get 2. Wait, how did I go from here to here? I said 1 minus AF is BF. And then yeah, something is weird here. Oh, wait, so, oh, you know what? I think I need to show this as 0 or something. Wait, the area of, yeah, but I'm not assuming the area of ABC is 1. I'm assuming that AB and BC and CA are 1. So basically I'm saying when I start with this and I subtract, so I subtract, oh, because I need to subtract this, and ABC. So I need to subtract another 1. So basically, I think I need to show this equals 2 instead of, yeah. So I want to show this as 2, not 1. Okay, because DEF, I take CED, then I need to subtract both of these and ABC. And after all that, then I need to get a 2. So yeah, okay. So the AE times BD is 1. And then we want to show that this part is also 1. So BF times AE plus AF times BD. And I wonder if, because AE or BF is just 1 minus AF. So that would be, okay, yeah, so the AE, yeah, so this should be 2. And then we know the AE times BD is 1. So yeah, we want to show this BF times AE plus BD times AF. And let's see, BD times AF is BD times 1 minus AE. Yeah, once we know this, I feel like it should help a lot. Oh, but we also know BF over AF. Yeah, we need to know something. I can divide it by AE times BD. So So if we take this fact and we use it here, then we want to show that, so I'll try that. So BD times AF equals 1. And then that's true if and only if. So you're saying now we want to divide by AE times BD. So we want to show BF over BD. Yeah, AF over AE plus BF over BD equals 1. And 8. It's very symmetric. You guys want to move on to the next problem and come back later, just because it's 10:30? All right. But yeah, interesting. I think we got pretty close there.